let's look at an example of satisfaction of formulas in the language of arithmetic. And let's take our standard interpretation or a standard model for arithmetic, so the natural numbers with the usual interpretation of the symbols. All right, and let us consider the following assignment. So let's say S sends X to 3, it sends Y to 4, and it sends Z to, let's make it 10. All right. Now, I'm not going to specify what S does to the other variables. Remember, you always have infinitely many variables. I could say, well, let S do something arbitrary to them, or send them all to 5, or whatever. But as we will prove a little later on, it doesn't really matter. As we had in the case of propositional logic, formulas are locally determined. So only the interpretation and of symbols occurring in a formula and the assignment to the variables actually occurring in that formula make a difference to its satisfaction or not. So now we haven't proven that at this point, but we will do so. And so then I promise you that we can do this with a clear conscience, and later I'll make good on that promise when we prove that. All right, so let's look at a couple of formulas. So the question, let's firstly look at something like there exists a x such that let's say let's not make it exist. Yeah, let's make it exist to x such that y times the success y times z is equal to x. All right. So let's think about this. Is this the case that in this structure under S, this formula is true? Now, to make or is satisfied. To satisfy this, I would need to find an X variant of my assignment such that what is in the brackets will be the case. So consider, let's think of this. How will I look at this? Well, I would need this x, whatever my x variant sends x to, would need to be equal to y times z. Now, this s prime will be an x variant, so what it does to y and z would be exactly the same as what s does to it. So what does s do to it? S sends y to 4, and it sends z to 10. So the value here would be 40. So I need to find an x that is equal to 40. So that's quite easy. So consider the x variant, that x needs to be a subscript. Consider the x variant s prime of s with s prime of x equal to 40. Then, well, consider s prime. Then I've got that s prime makes y times z equal to x. The structure n relative to the truth assignment s prime, to say this properly, satisfies this formula over here. Now this formula, why is this case? This is an atomic formula. So well, since what have we got here? The value in n under s prime of y times z. Well, what is that? That is 40, we said. That is equal to the value in n under s prime of x. So yes, so according to my definition, this formula is indeed, so under assignment S, or relative to assignment S in the structure N, this formula is satisfied. Next, consider this formula, number 2 over here, which says for all x, x times x is less than y. So let's see if this is true or satisfied in N under the assignment S. So let's think about this intuitively. This is saying for every natural number, if I times that natural number with itself, so that natural number's square is less than y. But now what is y under S? Y is set to 4. So this says the square of every natural number is less than 4. So that's clearly false. So let's see if we can show that using our definition of satisfaction. So to show that a universally quantified formula is satisfied in N relative to assignment S, I need to show that every x variant, x is the quantified variable here, every x variant of S, the argument of the universal quantifier, so the thing in brackets here, is satisfied relative to every x variant of S in the structure N. So I simply need to show that this is not satisfied under S in N, I need to come up with at least one x variant of S, such that relative to that x variant in N, this is not satisfied. So I need to find an x variant which sends x to something such that if I square it, I'm not going to get something less than 4. So particularly, I could take x as it stands, S as it stands, in fact. So I would say, well, consider in N under S, this is not satisfied because I don't have that x times x is less than y, since, well, what is x times x? Well, let's write it out. The value in N under S of x times x comma, the value in N under S of y, this is not, so let's do it quite formally, this pair is not a member of the interpretation in N of that symbol as, now, well, what is that interpretation? What's this value? This value is 3 times 3, so 3 times 3 is not less than 4, okay, because it's 9, all right? So I found an S variant of x variant of S, so I say, but S is an x variant of itself, and N relative to S does not satisfy the argument of the universal quantifier. So I get that N relative to S does not satisfy for all x, x times x less than y.